All right, so we are looking at section 4.2, the first part of that. We're looking at sigma notation and formulas to find sums. So the sum of n terms, a sub 1, a sub 2, a sub 3, can be written like this. It's the sum as I goes from 1 to n of a sub I. And so then we plug in these numbers. So we plug in 1, 2, 3. We only substitute in the integers between 1 and this number. So this I, this is called the index of the summation, and then this is called the lower bound, and this is called the upper bound, this number up here. So here's some examples of sigma notation. We have a sigma button on our calculator, but sometimes it's easier to just not even use that and just to figure it out. So we're going to just figure this one out. We're going to plug in 1 for k. So when I plug in 1, 3 times 1 is 3, minus 4 is negative 1. Plus, now I plug in 2, that's going to give me 2. I plug in 3, that gives me 5. Now I can see a pattern. See how the rate of change is 3? So I'm just going to keep on adding 3 every time. And so that's going to be written out, what my summation is. And now I can do it that short way that we just talked about Gauss doing. Because this is an arithmetic sequence, I can add these two and I get 13. Add these two, I get 13. These two, 13. So what's the answer going to be then? 13 times 3 is 39. You shouldn't need a calculator for that. Okay, for this one, a little bit tougher, but I'm just plugging in the number 1. 1 squared is 1 plus 1 is 2. Plug in 2, that's going to be 5. 3 is going to be 10. 4 is going to be 17, and 5 is going to be 26. There's no real shortcut way here because if I add these, I get 28, but if I add those, I get 22. I could do that though. 28 plus 22 plus 10, that's a little faster. That's going to give me 60. The other thing we want to be able to do is if we're given the sum, we want to be able to write it out using sigma notation. You don't have to always start with 1. So I could write this in sigma notation as the sum, and I can use any variable I want. Maybe I'm going to use x this time. So the sum as x goes from 2 up to what? 7. And what's happening to x every time it's getting squared? Now, what if instead of writing it that way, what if I said you had to start at x equals 1? Yep, you guys see why? We'd have to add 1 to our x and then square it. And then instead of going to 7, what would we go to? 6, right. So both of these would be correct. In fact, how many solutions are there to that? Infinitely many. You could start at 3, you could start at 4, you could start at 5, etc. Okay? But we usually just want to take the easy way. It's easiest if we just start that at 2. All right, looking at this one. So I can see again, this value is being added, added, added. Look what's happening here. The 3, the 5, the 1, 3, 5, 1, 3, 5, 1, 3, 5, 1. That part's never changing. What is changing is this. This is 2, then 3, then 4, then 5. So this would be then the sum, 3 is not changing, n over 5 plus 1. Because the 3 doesn't change, the 5 doesn't change, the 1 doesn't change. But then these numbers, what would be the easy way? Say n is going to go from 2 up to 5. So we need to be able to go in both directions. We need to be able to find the summation notation, the sigma notation, and we need to be able to write out the sum this way. Here are some formulas, and these used to be very important before we had graphing calculators because it would be a quicker way to find the sum. But anymore, these really aren't as important. Now, if you were taking AP calculus, you would have to know these sums in order to do Riemann sums and things like that. But we're not really going to get into that too much. So I just wanted you to have seen these sums for when you're in college if you have to do something like this. This is the one that Gauss actually used, so this is my favorite one. He actually, when he was adding those numbers from 1 to 100, what he did to find that sum, 1 plus 2 plus 3, he did this. He did n times n plus 1 over 2. So he used this. So his n value was 100. 100 divided by 2, not 5. 100 divided by 2 was 50. And then his n value was 100 plus 1 was 101. Remember how he got 5,050? So he was really using this formula back when he was in 3rd grade. And Gauss went on to be a famous mathematician. He did a lot with both math and science. There's like some Gaussian laws in science that are attributed to him, so he was a very intelligent man. All right, so now we're going to use the formulas, and I'm going to show you how to do this on your calculator. If you have a newer calculator, you're in luck, because you just have a summation key on your calculator. You have that sigma. So everybody check right now. Go under math and arrow up and see if you can get summation. Does everyone have the summation? Does anyone not have summation? Raise your hand if you don't have it. Okay, I'll go through it if you don't have it. So if you do have it then, to do this problem, all I'm going to do is, if I want to use the letter I, I can, but I always change i's to x's. X goes from 1 to 20 of 3x. And so this answer is 630. If you forget your calculator on the day we have a quiz, or if your own calculator doesn't have summation, so one of these older ones, if I go to math and I arrow up, see how there's no summation there? So here's what I have to do. I have to do the sum of the sequence, 3x. My variable is going to be x from 1 to 20. You don't even have to use that number 1 I found. So here's what I have to do to find sum. Sum is under the catalog. So to get to catalog, I'm going to have to do second 0. Now I'm to the catalog. I have to jump down to the s's. So to do that quickly without having to arrow, I'm just going to look for the letter S, push that button, takes me here. So now I can scroll down to sum. So there's sum, so I want the sum, and now I need the word sequence. So rather than going under all these menus and trying to find sequence, I can go to catalog again. And I'm going to jump down to my S's. See, everything we have on the calculator can be found under the catalog, every command. So we've got the sum of the sequence, and now we say 3x. Here's the comma, right here above the number 7. And then I tell it what my variable is, x, comma, and this is from 1, comma to 20. And I don't think you need the 1 after that. And it tells me that sum is 630. So it's a lot easier to do if you have the newer calculator, of course. Are you glad you have the summation on there? Yeah. And then you're going to have to do that? Yeah, that's no fun. Okay, I'm going to do this one the hard way. If you have the easier calculator, go ahead. I go to catalog, and I'm going to jump down to my S's. So I want the sum. Then I have to go back to catalog, go to my S's. You guys are probably already finished with the newer calculators. Sum of the sequence, and now I have to put in my function. So my function is x squared plus 5, comma, my variable's x, comma, from 1, comma to 20. And you get 29.70. What's that?
On the thing it has another one doing that.
You do not need this one. Mm-mm.
Is that it?
Okay. Now, we have another little part here, guys. I want you to look at this problem that you're going to have on your homework. So this is it, so you don't have to flip into your book. This is on page 262. We're going to do number 23 here. So your directions will say, in exercises 23 to 26, bound the area of the shaded region by approximating the upper and lower sums. Use rectangles of width 1. The whole reason we're learning about summation is because integration finds the area under a curve. You don't need to write this down, but if I have any kind of curve, if I know the function for this, and if I can find the integral, what the integral does is it makes these infinite number of rectangles, and it finds the sum of all their areas, and then it can find the sum under the curve. That's what integration does for us. So right now we're starting with one way to approximate the area under the curve. We're trying to figure out about what this area is right here, bounded by the y-axis, the x-axis, and this curve. So first we're going to do an upper sum. Upper sum means I'm going to look at this rectangle of width 1. I'm going to go above the curve. I have to either use this point or the second point. This point that's above the curve would be if I made the rectangle using this point. So this would be my first rectangle. You can just watch this. You don't need to write it down. On this one, I want the rectangle that's above the curve. So am I going to use the first point or the second point? Second point to go above the curve. What about on the next one? First point or second point if I want to go above? Second. And then on my third one, first or second? I have to use the second, right, to go above the curve. So I always had to go above the curve to find the upper sum. So now I need to find this area. So this width is 1 and this height is 3. So what's the area of that first rectangle? 3. So it's 3 plus. What's the area of this rectangle? 4 plus. What's the area of this rectangle? It goes up to 4.5. So it is 4.5. And then the area of this rectangle? 5. So my upper sum then is going to be 7 plus 5 is 12, plus 4.5 is 16.5. That's our upper sum. Okay, now we want to find our lower sum. So our lower sum is the same thing, except now we're going to go below the curve. All right, so I'm going to look at my first one here. I have to either use the first point or the second point. To go below the curve, I'm going to use this point to stay below the curve. I have to use this one or this one to be below. I'm going to use this one. I have to be below, so I'm going to use that first one. And then below, I'm going to use that first one. And now to find the lower sum, I'm going to have to compute those areas. So what's the area of this little rectangle? 1 plus, what's the area of this one? 3. What's the area of this one? 4. And what was the area of this one? 4.5. And so my lower sum then is going to be 8, 4.5, 12.5. So these are estimates for the area under that curve. But what's wrong with finding the upper sum? It's going to be what? Too much. And the lower sum is going to be too little. So with calculus, we make these rectangles even less wide. We make them as narrow as possible, and then we get a very good estimate. But we could also get a good estimate by doing what with our upper and lower sums? Averaging them. So what would be a good estimate for the area? Right. Estimate for the area is 14.5. But like I said, later we're going to talk about how the integral from 0 to 4 of that function, that would actually tell us, not equals dx, of dx, that is going to equal the exact area. Okay, so that's what we're going to do later. But first we have to understand summation and how these are going to be pretty good estimates for the area of the curve. All right, so you've got your assignment up there. I did shorten it a little bit because I don't think all those were necessary that's on your assignment sheet. So you can just do 1 through 10, 24 through 27.